Hello and welcome. In this tutorial, we will take this Excel worksheet, extract meaningful information from it, and wrangle it to get this analytic data set. We will then create a relational SQLite database and store our data in it. You can take this as a mini data wrangling project in R, trying to create a data pipeline for your analysis. The task of data preprocessing is an essential one that a data scientist would have to master and enjoy, because it is known to take much of the analyst's time. The quicker you can do this, the faster you get to the insight in your data. Also, if the analysis is going to be error-free and the insight is going to be rich, then preprocessing the data has a lot to say about those objectives. This is all the code we will write, but we want to do so with meaning and understanding. This is what you will learn in the process: how to think through a data cleaning task in R. Your ability to reason around the task of data cleaning is far more important than the tool you use. You will learn to automate repetitive tasks via a function. This is our way of processing similar data and not start from scratch. You will learn to pick simple and robust approach for a given task. Also, we will come across missing values, so we will justify why we exclude them from our data. You will experience practical data manipulation with dplyr package. However, we will get to know how to implement the same data manipulation skills in base R. So do not worry if you are not a fan of packages or you want to improve your base R skills. There will be regular expressions to at least stimulate your interest in knowing more about them. Imagine having this data for the first time. You need to understand it and wrangle it. What part of the data do you keep or remove? What will be your rationale for the decisions made on the data? Remember, R is just a tool we use to implement our thought about the data. This means what is important is the analytical mindset. And in this tutorial, we will justify all the actions we take on the data. I will be using RStudio IDE for convenience, and you do not need it to follow along this tutorial. And our script is going to be an R Markdown file. To run a code chunk, I may click the Run command here or use the keyboard shortcut Ctrl-Enter. By the way, using the Insert command here or via Ctrl-Alt-I, this will insert an R code chunk. A code chunk is just a group of R code we can execute together. We will be using functions from the tidyverse package. However, I will also show you the code you can use if you are all about base R. I will strongly encourage you, though, to at least try the tidyverse package. The strength of R is in its contributing packages, and tidyverse makes manipulating data intuitive and fast. You may also want to try the faster data.table package, but we will not use it in this tutorial. To tell R we want to use the functions from an installed package and almost always not refer to the package name, we can use the library function, pass the package name as an argument, and run that line of code. You should see that tidyverse houses other packages like dplyr and string-r. What you see here are the core tidyverse packages. If you want the full list of packages in tidyverse, you can run this line of code. Let us now explore the Excel file we will wrangle. There is a header here containing the report date and the location. We have a pie chart and then a general data of 5 columns: code, description, and others. Our data can spill over into another report page. We will see very shortly how R will handle this Excel file. We use the read_Excel function from the readExcel package. Since readExcel is not a core tidyverse package as at the time of recording this video, either we load it separately or access the read_Excel function using the double colon operator. We will pass the full path of the file as argument. Here, just the file name is enough since the file is found in the same folder as our current workspace. The read_Excel function returns a data frame, specifically a table, and we will assign it to a variable df. Let us simultaneously print it by enclosing the assignment in parentheses. We run that chunk of code. That is cool. We see the columns, code, description, and others that we saw in the original Excel file. But there are also new columns that perhaps were hidden in the Excel sheet. Those columns did not have headers, so read_Excel used 3 dots and the ordered number they appear to label them, column 3 to 8. Column names in our data frame can be accessed as if they are variables in our namespace. This means they must be valid variable names. A variable in R cannot have spaces in its name, and hence the % followed by space and some characters is not a valid name in R. Though you might not see it in the R Markdown output, R puts backticks around it to indicate a non-standard name. Let us rename it. We take the data frame and pipe it into the rename function, but we will use just % to replace the non-standard name. We then assign the data back to itself and then print it. When we run that code chunk, we have our column names standardized. We can now take a glimpse of our data. To have a summarized horizontal view, we have 30 rows or records and 11 columns or fields. Some are of character type, logical, and double. Checking the data types of your columns is important because that at least restricts the type of computation you can do with a column. For instance, you do not want to perform arithmetic with a column which is not numeric. It seems some of the columns have all Mason values, NAs. Instead of inspecting the columns with our eyes, we can count the number of Mason values in each column. We take the data frame and pipe it into the summarize function. We use the across function to select all the columns and apply SumIs.NA function to each of them. This returns a wide formatted data frame, and we can use the pivot_longer function to reshape it into a longer formatted data frame. It is now easy on the eye. We could have used the scope variant summarize_all function, but it is being superseded by the across function. We see that columns 3 to 6 have 30 Mason values, the same as the number of records we have in our data frame. This means we can drop those columns. They have no column names and no data. These are just blank hidden columns placed between two visible columns that have data in our Excel worksheet. And our read_Excel function could not recognize that and read them as part of the data. We will be checking for Mason values in our data again, so let us wrap these steps in a function. I will call the function na_info. Let us also test it on our data frame again. Our function works. We get the count of Mason values in each column. Columns 7 and 8 also have no names and each has 10 Mason values. We will select just those columns and then filter for records or rows that have Mason values. We see that the two columns do not just have the same number of Mason values, but observations with Mason values are the same for each column. The two columns seem to go together. Let us look at our original data frame again. Column 7 seems to be like the code column. For instance, the code R01 can be found in both columns. We see 3 of them in the first column and perhaps only one in column 7. To investigate if the two columns have the same entries, we can find the distinct entries in the code column. We do not want the Mason values, so we drop the NAs. We will do the same thing for column 7. They both have 20 distinct codes. It seems column 7 is the same as the code column. We can check for equality of entries within these two columns. This will return a logical matrix or array, so we use the all function, which will return true if all the entries of our array are true and false otherwise. And when we run it, we get true. Now we know the code column and column 7 are related in some way. They have the same distinct entries. The percent column, if we should pull it as a vector and sum with NAs removed, we get 100. It makes sense because it is a percentage column. We will do the same for column 8 and we get 100 as well. This tells us column 8 is probably sums of percentages. Probably when the percent column is summed for each code, the result is column 8. We can explicitly check that. We take our data frame and group by the code column and then tally the percent column to find the sum of percentages for each code. We will drop any missing value and arrange the counts in descending order. Our suspicion is that this is the same as selecting column 7 and 8, dropping missing values and arranging the numeric column. Let us see what this gives us. We get the same data frame for each of them. Code R01, for instance, has about 59.37%, and it is the same when we look at the other data frame. This means columns 7 and 8 are aggregated fields which we can always compute from existing columns, the code and percent columns respectively. And so we can drop columns 7 and 8 without losing any information. We will now take our data frame df and deselect all columns that have this pattern, 3 dots followed by a digit. That is what the \lowercase d means. The minus sign before the matches function indicates our intent to remove those columns. We will assign the resulting data frame to a variable dt. Let us also print our new data frame and check for missing values. There is our new data frame. We have removed all the columns we do not need, but we still have missing values that we must deal with. We need to understand those records with missing values before we decide on what to do with them. We take the data frame dt and pipe it into the filter function, but this time we use the if_any helper function to consider any column with missing values. We see that this corresponds with the count of missing values in each column. For instance, all the 2 records have missing code, description, and percent, and 1 record is missing count and hours. That is exactly what we see when we look at what our na_info function returned. However, there is 1 record with all missing values, and if we are interested in filtering for just such records, all we need to do is to change the if_any helper function to the across function. We have an entire observation missing. Unless we want to understand why, we can drop that record and pay no penalty for doing so. The dilemma is what to do with the record where count and hours are not missing. Let us go to our data frame and see if it will give us a clue on what to do. We want to find the index or which row the missing values occur. We have just a few records, so we can manually inspect. It occurs at the last record. However, we will not have the luxury to scroll through our records to find the index with missing values if there are many of them. So let us find a reproducible way to do this. We will convert the row names into a column using the row names _to_ column function and then filter for records with missing values. The last record is where the count and hours are not missing. Since our data is coming from a Microsoft Excel report, the last record will probably be an aggregation, but what type of aggregation, if indeed it's an aggregation. Let us test our aggregation assumption of the data using two common ones, sum and average. We take dt and with the help of the slice function, we get all the records except the very last one. The function n computes the number of rows, and this coincides with the index of the last record. The negative sign excludes that record. We will summarize across the count and hours columns and compute the sum and mean. We need to remove the all NA record we know occurs at row 29. And when we compare this with our data frame, the value for the count column in the last record is 220, and it's the same as our sum. The same thing can be said about the hours column. Basically, we have established that the last record is an aggregation, and we can ignore. So let us drop all the NAs in our data frame. We now have a data frame free of missing values and unwanted columns. Let us encapsulate all our steps into a function. We will call the function clean_data, and it accepts the path of our Excel file. We read an Excel file into R and then rename the non-standard column. The extra columns our read_Excel function captured are either all missing or can be aggregated from an existing column, so we deselect them, and then we also drop records with missing values. Let us try our function out on our Excel file. We get a clean data with no missing values, and we have excluded all irrelevant data. However, if you remember, the original Excel file indicates the date for the report and the location. But we lost all that information when we read in the data using read_Excel function. This is because read_Excel reads rectangular data that appear in the cells of a worksheet. The date and the location appear in the header of the worksheet. But we need to find a workaround. Thankfully, there is a package called Openxlsx that can help us. You can install it and load it using the library function. Let us check the functions that come with this package. It contains quite several functions, and obviously it does more than just reading data stored in Excel Workbook. We will try the read.xlsx function on our file. Unlike the read_Excel function from tidyverse, this seems to give us a nice data frame to start with. So why did we not use it in the first place to read in our Excel data? I wanted us to improve our data cleaning skills, and using the read_Excel function from tidyverse gave us the chance to do more data cleaning, making decisions on the part of the data to keep and what to modify. Besides, the read_Excel function is about 2 times faster than the read.xlsx function, and we can see that when we micro-benchmark the two functions on our Excel data. We want to get the report date and location. We will use the load workbook function from the Openxlsx package. This returns an entire Excel workbook with all the various components, the chart, style, formatting, and the rest. We can explore the structure using the str function. What we want is the first worksheet because that is where our data is. The location and date are in the header of the worksheet. Excel worksheet header is divided into 3 sections, and we want the middle or center part, so we subset for the second. We will call this header. This gives us a character vector with the information we need, the date and the location. Though it is a little bit messy, we can extract the part we need. Here, regular expressions may be handy. It is a good idea to remove unwanted spaces from the end of a string, particularly useful if we want to extract strings that appear at the end of a text. We use the str_trim function for that. Before we think of any serious regular expressions, When we look at our header string, it seems the components are separated by white spaces, and we can split it using whitespace \s as the pattern. This gives us a one-element list. We can get the content as a character vector using the double bracket. The third entry is our date, and the fifth is our location. The date, though it is in a square bracket, it can easily be passed as an actual date using a function from the LibreDate package. However, whenever we have a location with spaces in the name like South Africa or United States of America, then splitting on a space will make each of the name components occupy a different index in our character vector, and we need to find a way to combine them. But we can be a little bit robust in getting the location and the date. We will use the str_extract function to extract the location from the header using this regular expression. First, we know that our location is whatever comes after the word location followed by a colon and a space. The question mark followed by less than or equal to in our regular expression is a look behind assertion, which means we will get Brazil provided what is behind it is the word location followed by a colon and then a space. We put our look behind expression in bracket to treat it as a group, and the period followed by plus matches one or more of any character. Also, whatever is enclosed in square bracket is the date, and we can extract it from the header using this pattern. You already have seen the question mark less than or equal to, which means we want to look behind for an opening square bracket. The question mark equal to is a look ahead assertion, meaning whatever substring we want to extract should have a closing square bracket after it. Realize that both opening and closing square brackets are special regular expression characters, and because we want to treat them as literal strings in R, we use double backslash to escape them. Let us print out the location and the report date. We have what we want, and that is good. We have a function that cleans the data, so we use it on our Excel file. What we will do next is to create two additional columns by mutating our data frame with the report date and location we extracted. Our resulting data frame should have two extra columns. Our date is a string. We can change the type to an actual date using the mdy function from the LibreDate package. If you have tidyverse, you also have LibreDate, but it is not a core tidyverse package. So we get to the mdy function using the double colon operator. We are using the mdy function because our date string is in the form month, day, year. We will also make all our column names lowercase via the rename_with function. This gives us exactly what we want. We will encapsulate our steps so far as a function. We call it get_header_info, and it takes the Excel file as an argument. We use the load workbook function from Openxlsx to read the file and then get the string in the header of the first worksheet. We already know the regular expressions for extracting the report date and location. We want to get all of them simultaneously, and so we pass all of them as a vector. The str_extract function is vectorized over the pattern, so this is allowed. This will return a character vector with the first entry being the date and the second being the location. We can use our get_header_info function on our Excel file and run the code chunk. We get the date and the location as a character vector. So far, so good. Let us write one more function that puts the steps of cleaning the data, getting the location and report date, as well as adding extra columns together. It is a good idea to write functions for specific tasks and then combine them to solve a complex problem. We will call the new function transform_data, which takes the file we want to transform as argument. The file gets passed to the get_header_info function for the date and the location. We take our clean data and pipe it into the mutate function and create 2 extra columns. Remember, the report date is the first in our date_log vector, and we convert it to a date since it is a character. The location is the second in our character vector. Finally, we turn the column names into lowercase. Let us try it out on our file. We get a transformed data ready to be analyzed or stored. The last thing we will consider in this tutorial is to create SQLite Database and store our data frame as a table in that database. SQLite is a lightweight database file that sits on your computer. To get it in R, we install the RStudio package and then load it. We can use the ls function to see all the objects that it comes with. If you have used the dpi package in R before, some of the functions like dbconnect might be familiar to you. dbi is just an interface that the backend RSQLite implements, so it is trivial that the function names in dbi are also in RSQLite. Now, to create SQLite database in R, we just need to connect to one, and if it does not already exist, it gets created. So, dbconnect, we want to use SQLite driver, and we will call our database time_code_info. As soon as we run that code chunk, we have our database created, and we also have connection to it. Now that we have created and connected to a database, though we can use the functions from RSQLite or dbi package, we want to continue using functions from tidyverse, specifically dplyr package, and I will also show you the corresponding dbi or RSQLite functions. We need our transformed data, and we will call it db_final. We will copy this data frame into our SQLite database using the copy_to function. We give it the connection, and the name of the table is going to be our _code. The data frame is now sitting as a table in our database. We can use the tbl function to reference the table. We will call it db_df. The printout is just a view of the table in our database. Using functions from dplyr package, which is part of tidyverse, make us work with database using the usual tidyverse semantics instead of writing SQL queries. However, I will encourage you to learn SQL if you intend to work with databases. For instance, we can summarize our data by finding how many codes are present and then arranging the counts in descending order. This gives us what we want without writing any SQL. dplyr lazily takes care of the SQL for us. We will end it here. This tutorial was to get you to improve your data wrangling skills and introduce you to SQLite Database in R if you want a relational way of storing your data after cleaning it. A quick recap. We took an Excel file as a data frame in R and cleaned it. We also extracted specific information from the Excel file and mutated our data frame with that information. We created SQLite Database and copied our data frame as a table. In all these, we were interested in how to think about data pre-processing problem and how we frame a robust, reproducible solution. You may want to subscribe and share the video for others to benefit. Thanks for watching.